Thank you, Stephen, and thank you all for coming this morning. I'm excited to share with you the culmination of not just the 4 years of my Ph.D., but really going back about 9 years, starting with my master's that Stephen spoke of. So today I'll be going through a little bit of background on freshwater salinization, and especially as it relates to coal mining in my study systems. And then I'll discuss a little bit about the prior research that led me to my doctoral work, as well as an overview of the study system in which I've been working. And then I'll cover the 3 primary chapters of my dissertation, and then we'll wrap it up with some conclusions. So freshwater salinization is a global concern for freshwaters that have come about from a variety of human activities, such as road salt application, water abstraction, irrigation, and especially, as concerns my research here, is surface coal mining. And when I say freshwater salinization, I'm simply referring to the elevated major ions of calcium, magnesium, sodium, potassium, sulfate, bicarbonate, and chloride that occur in some proportion naturally in surface waters, but can become quite elevated and therefore toxic when some of these activities take place. And when that happens, it can manifest in a number of ways, primarily aquatic biodiversity being the concern of my research, but also things like ecosystem function, which are the processes like nutrient and carbon processing in streams and rivers and lakes, as well as ecosystem services, the things that humans benefit from, such as fisheries, for example. It can also lead to human health and economic impacts when potable water becomes contaminated or the costs of treating that water become really high. This is an issue that's been getting more attention of late, and here's just a couple of papers from the past couple of years that are addressing the issue of salinization. And in fact, there's a couple of folks here. John Dobeck is part of the IGC group who's been part of a study with some fellow students on lake salinization from road salt application in the Northeast and in northern latitudes. And then there's this Timpano fellow over here. So in the U.S., we have a number of biodiversity hotspots, but in our region, especially the Central Appalachians, is quite a notable region right here in southern West Virginia and southwestern Virginia. Unfortunately, as it happens, we also have a lot of coal in that region. And here's the Appalachian coal field, and in that oval that I've depicted is this 80 by 200 square mile zone, and all these little white specks you see are not clouds, but are barren land that are being actively coal mined. And there's probably much more that you can't see because it's been revegetated. So with coal mining, and here's an example of about a 50 square mile mine, so that the impacts can be quite extensive. And then here is what is called a valley fill, wherein they take all the rock that was on top of the coal and they dump it into a stream channel. It flows through a small sedimentation pond and then into the stream and into the receiving waters, and that's where the primary source of salinization is. And with surface coal mining, especially in my study region, I'm concerned primarily with these 4 components of the major ions: calcium, magnesium, sulfate, and bicarbonate. The sodium, potassium, and chloride can also be elevated, but in my systems, they are not as prominent. Now, to measure these ions, I can take water samples, which I've done, but it's a very time-consuming and inefficient way to go about it. Instead, what I've done is I've measured this surrogate known as specific conductance, which is the electrical conductivity of the water that's been standardized to 25 degrees Celsius. And as the concentrations of these major ions increase, the electrical conductivity of the water increases. So it's a very robust and reliable way to quickly and economically measure the ion concentrations. And so for some perspective, in unmined streams of the region, we're quite dilute, 20 microsiemens to about 200 microsiemens, which is about the upper limit of reference streams across the United States. So most waters are fairly dilute. Just as an example, I believe Blacksburg tap water is in about 120 or 150 microsiemen range. Whereas mine streams in my region can be an order of magnitude or greater above that, which presents concerns for aquatic life. Now, benthic macroinvertebrates are the group of organisms that I've been studying. I'm sorry, hang on one second. Okay, sorry. So the group of benthic macroinvertebrates are primarily aquatic insects of concern. They're critical components of the ecosystem. They process carbon, they process nutrients, they provide biomass, they provide food to just about any predator that's associated with a stream environment, both aquatic and terrestrial, such as spiders and bats, for example. And these are some of the main folks of interest: the mayflies or the Ephemeroptera, the stoneflies or the Plecoptera, and the caddisflies or the Trichoptera. These are 3 orders of insects that are typically associated with pollution, and because of that, they're used throughout the United States and globally as good indicators of that. And here in the U.S., we have regulations. We have the Clean Water Act, which requires protection of aquatic life. And EPA has chosen to use this group of organisms to define that endpoint. And over the past decade, they've made 2 attempts to develop guidance to address salinization in freshwaters. However, as of this moment, we're still in draft mode. We're not fully vested in terms of regulation. So there's a lot we still can learn and need to learn, in my opinion, to fully understand this issue. So my prior research was a first cut at trying to understand this issue, wherein I used a Virginia Biotic Index score, which is simply an aggregate measure of the biodiversity of these aquatic insects. And the higher the value, the more undisturbed or more reference-like that is. So that's what's considered an ideal situation. And as we increase in conductivity in the streams, that index score declines, which is, in a regulatory sense, undesirable. So it's a good indicator of the impact, but we see a lot of variability, as you can see about that fitted line, which got me thinking. There are some elements of the current approach that could explain that variability. One is what I call the snapshot approach. So what's done is bioassessment surveys are conducted generally seasonally, either in the spring or fall or both. And the biological community is sampled concurrently with the water quality. And then those 2 are used to be related to one another to develop the association. However, in doing so, there's no accounting for temporal variability of either biology or water quality. And we know things like annual hydrologic cycle affect stream flow and concentrations of stream solutes, as well as the organisms that have roughly annual, in many cases, life cycles. As they're growing and developing throughout the year, they may be exposed to different levels of salinity that may affect them differently. So I got incredulous since I couldn't figure out how in the world we can talk about what's going on in a stream from only 1 or 2 measurements. So that led to my research questions, the first of which is, what is the annual pattern of salinity? Obviously, the implied question is there a pattern? But assuming there is one, what is that pattern? Secondly, can we use this technology of high-frequency conductivity monitoring to improve our ability to predict biology, which is an important consideration for resource managers seeking to mitigate these effects? And then finally, what is the association between salinity and the benthic macroinvertebrate community? Bottom line is, what level is causing, or what is most likely to be causing, deleterious impacts? So I embarked on an epic data collection effort over the past 5+ years, working in southwestern Virginia and southern West Virginia, wherein I had about 25 streams, all first order, all affected by those valley fills or some form of mine spoil that I showed you earlier that have become salinized. And then I used a standardized, what they call rapid bioassessment approach that's widely used by EPA in the States to sample the benthic macroinvertebrate community in spring and in fall. And then into the streams, I installed these automated conductivity data loggers that recorded conductivity every 15 or 30 minutes in each of the streams over that period. One of the really important elements of my study that I spent hundreds of hours to ensure was high quality in-stream and riparian or streamside habitat. This middle stream is one of my reference streams that happens to be the lowest salinity of all my streams. It runs about 25 microsiemens. It's quite dilute. And then the other 4 streams are 4 of the highest conductivity or salinity streams in my system. And what you'll note is that all of the streams have a well-developed forested riparian zone, which is critical for affecting evapotranspiration in the water that's coming into the stream, as well as the other components such as the leaf litter and other materials that contribute to a fully functioning ecosystem. And in addition, the in-stream habitat is quite diverse. These organisms need a good mix of particle sizes and places to hide and live. So one of the problems with mining can be excessive sediment deposition, so fine sand and silt, which can smother habitat, but fortunately I was able to avoid that. So for all of my research, I used the same data set, which is these benthic macroinvertebrates and snapshot conductivity every season over this period here. And then I use continuous conductivity every 15 or 30 minutes for about 4.5 years, which is about 3.4 million records of conductivity, as compared to the snapshot method, which gives me 8. So quite a difference there. And I did that for all 25 streams. So the first phase of my analysis involved the salinity patterns, wherein I sought to quantify the annual salinity pattern, number one, but then to evaluate alternatives to that pattern, because let's face it, putting a conductivity logger in every stream is probably not practical. In addition, there's already monitoring efforts that are being conducted manually that may suffice to provide the information necessary. So I wanted to examine alternatives there. And the rationale being that we know from other research into stream processes that stream flow changes throughout the year, which in turn affects dilution of these salts. So we know that varies annually. And so I felt like that was going to be a contributing factor. And just as an example, here is Panther Creek, West Virginia, which was one of the smallest, was the smallest stream that I could find that USGS has a gauge on in my study region. And as you can see, we have a up and down flow pattern throughout about 4 years here, which appears to be roughly seasonal. And as it turns out, I got lucky because this stream actually is a receiving stream to my West Virginia reference site. So that was quite fortuitous. So if I look at 50 years worth of daily average stream flow, we see a clear seasonal pattern with a highest flow in the late winter, early spring, and then a low flow in late summer, here September, and then the cycle continues. Which looks a bit opposite to my conductivity data. So this is an example of one salinized stream, specific conductance on the y-axis, and time about 4 years here on the y-axis, or excuse me, x-axis. And you can see that we have this general seasonal pattern with these abrupt, what I'm calling dilution spikes, which occur from rain events. By contrast, we have a reference stream, which is much more dilute. And you can't see it from this pattern, but I assure you it follows a generally seasonal pattern as well. Now, I needed to be able to compare all of these different sites at different salinity levels, but I can't do that directly. So what I did is I converted each site's values standardized against its mean. So I calculate the mean conductivity level for a site, and then I take daily values and convert them to relative deviation from that mean, to where I get approximately, say, 20 or 30% higher than mean in the fall up here, and then about 20 or 30% lower than mean in the fall down there. And that way I can standardize across sites. And when I do that, aggregate across 25 sites in 4 years, I get one sinusoidal model like this that shows the annual cycle. Quite strong model fit, little bit of deviation here in the fall, but because that can be a bit of an unpredictable time between leaf fall and the onset of fall and winter precipitation. But it fits fairly well in terms of the overall model. And we can see that we indeed have a quantitative minimum in the spring, which is about late February, and a maximum in the late summer, early fall. This is about late August, I believe. And we do indeed have about a 20% deviation on both spring and fall, 20% higher than mean in the fall and 20% lower than mean in the spring. And this has significant implications because in the past, with only one or maybe two measurements a year, that value of conductivity was ascribed to that stream. So what is the conductivity of a stream? Well, it's whatever we measured, say, here in April, which is unrealistic given what we know about how this varies. So if you measure a mean of 1,000, you could be 800 in the spring or 1,200 in the fall, which has implications, especially if you're setting water quality standards. Now, this pattern, it turns out, is natural. It's not an artifact of coal mining because when I examine the reference streams in the gray line by themselves versus the test streams in the black line by themselves, they follow roughly the same pattern with very minimal differences, only about 12% difference in amplitude and about 8 or 9 days difference in the timing of when those minimum and maximum values occur. So that was reassuring because we didn't know going in what to expect in terms of the pattern. Now, in terms of alternatives, what I wanted to do is I wanted to simulate other sampling intervals. And by doing that, I took my sampling interval of 1 day, which is what I just showed you in the previous plot. And then I simulated less frequent sampling at 7 days, 14 days, 30 days, 60, and 90 days. And then what I did is I calculated what's called prediction error. And that's just the span of the prediction interval around the fitted line. And as you can see, we're relatively low for about 30 days, and then we start to ramp up rapidly, which tells me that sampling intervals beyond 30 days start to increase our error rapidly. And here's an inset of just 1 through 30 to show you that with our sinusoidal model that I just showed you previously, we're about 14% prediction error, which isn't really low, but it's the best we can do with the model that we have. And we can stay below 20 roughly if we stay within 30 days. So that was a significant finding that anything, quarterly sampling just isn't going to cut it, it doesn't look like. So in summary, I was able to quantify the salinity pattern wherein I saw a strong sinusoidal cyclic pattern throughout the year with a minimum in spring and a maximum in fall, about 20% deviation from mean. And this is important because it allows us to predict that conductivity for management purposes. And then secondly, in evaluating alternatives, I found that if you keep the sampling interval to 30 days or more frequent, you're minimizing your prediction error, which is the ideal scenario. So in the second phase of my analysis, I wanted to evaluate the traditional snapshot approach relative to this new continuous conductivity approach, and to see if one could predict biology better than the other. And my rationale for that was simply that the continuous conductivity data allows us to talk about the salinity that the organisms are exposed to throughout their life cycle. And there is research to suggest that there may be more sensitive stages, such as when the insects are in the egg form, for example, or when they're newly hatched, as opposed to being more mature. So in order to do that, I had to calculate community metrics. And these are simply metrics that are based on the richness, which is the number of different species, for example. I used genera, which is 1 level removed. Relative abundance, so how numerous are the individuals. Diversity, which is a combination of the two. And then evenness, meaning how many of the individuals in a specimen are attributed to 1 or 2 really abundant species, which is uneven, as opposed to most species being relatively consistently distributed. And generally, more natural systems are more even. Unevenness is a sign of alteration, typically. In order to do that, I had to have 2 independent variables. One was the snapshot conductivity, for which I had, I'm just going to focus on spring, by the way, for brevity's sake, and because that was the strongest associations I found. And then continuous conductivity, for which I calculated the monthly mean values of each of the months in the 12 months prior to sampling. So for spring, I sampled in April, basically, mid-April for most samples. And so going back 12 months prior to that, for the prior year, I was able to calculate mean conductivity values using my continuous data. And I fit those in a generalized additive mixed model with each of those different conductivity predictors. And that allowed me simply to correct for the fact that I've been to each of these sites and collected samples 4 times repeatedly over the course of the study. And then in order to estimate model fit differences for comparison purposes, I bootstrapped the confidence intervals of the R-squared values. So to start off, this is what the model fit looks like. Here we have total richness, which is the total number of different genera of insects, benthic macroinvertebrates that I found in the sample. And then specific conductance here, again, this is just the snapshot. This is just the value at the time of biological sampling. And we can see a distinctive negative trend, but then it kind of flattens out once a lot of the sensitive organisms have been extirpated or have disappeared from the system, or at least weren't in a sample. But it's still, a good bit of variability and a moderate R-squared. If we look at an alternative metric, which is just the Ephemeroptera richness, those Mayflies, so the number of Ephemeroptera genera, which tend to be more sensitive, appears to be the case. We have a much steeper, much tighter fit, a much higher R-squared, to show that that group declines relatively rapidly with increasing conductivity. Now, in order to compare the snapshot to the alternative prior intervals, what I did is, like I said, I bootstrapped the confidence interval. So here we have our snapshot value. This is the point at which the biological sample was collected, as I said, generally in April. This is my dependent variable for all of these models. And this is just the confidence interval of that value. And then I look at the prior water quality for each of the monthly mean values for the prior 12 months, and I do the same thing. And so what I get after running 10,000 bootstrap simulations for each, I get these confidence intervals. And I'm looking for lack of overlap of confidence intervals. If I don't have overlap of confidence intervals, I can be confident that they are statistically significantly different. And I don't have that here. I see some nominal differences. There are some slightly higher and some slightly lower model fit values. But generally from this, I can't conclude that snapshot or any of these monthly mean values are better than one another. And I can do the same for my other example metric. This is the Ephemeral richness metric. Again, we have higher R-square values in general because it is a more responsive metric. But my snapshot value, while being generally one of the highest, is not significantly different from any of the other values. So in summary, I didn't find any significant differences between those values. However, I'm not entirely surprised by that because I know that the predictors are highly correlated with one another, a mean correlation of 0.96. And that's not surprising if we think back to my sinusoidal model. If I measure conductivity here, it's going to be correlated to conductivity here, 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 or here, for example. So that's not terribly surprising. However, I think part of the reason also that I didn't have differences is that my quote-unquote snapshot data are atypical. I think they're quite exceptional with how consistently they were collected. Just to show you what I mean. My samples were collected roughly late March to, I think May 1st was the latest I had. So about a 40-day window when I collected those samples. Most of my samples, however, were even tighter than that, about middle of May with about plus or minus 4 or 5 days. So very consistent over all 4 years. Whereas other collection scenarios may vary. For example, in Virginia, there's a 90-day window, March through May, during which those organisms and consequently the conductivity values can be collected. Contrast that with West Virginia, which uses 7.5 months all summer long, March through early October. So in other scenarios, when snapshot, quote unquote, snapshot data are collected throughout the summer, for example, there's a good possibility that variability could be higher. So for the final phase of my analysis, I wanted to examine what exactly is the benthic macroinvertebrate response to salinity. So I had 4 objectives. The first 2 were related. 1, characterize the community level response. Those biological metrics that I showed you a moment ago are really commonly and widely used, but they don't get at whole community level response. And then in addition to that, I wanted to identify which members of the community were most sensitive relative to others. And for that, I used non-metric multidimensional scaling ordination technique, which is a multivariate technique that allows me to look at the whole community together. And for my other 2 objectives, also related, I wanted to model those community metrics that I just showed you to understand how the different metrics respond to conductivity, but then also determine the levels of conductivity that were associated with change from reference, because that's how generally it's approached in the United States especially to determine when we have undesirable conditions, is when things start becoming different from reference condition. And for that, I used the generalized additive mix modeling that I showed you. So for the first phase, I took all my site data. I took my about 60 genera, different insects, and I took the abundance data, and I converted that to what's called the Bray-Curtis dissimilarity index. And that's simply a measure by which it explains that the sites are different or similar to one another, essentially. And then the ordination takes each of those points, I have 194 samples, and tries to arrange them in space to best represent the differences from site to site. And what I saw is a distinct separation by season. My spring data separated out from my fall data, which is not something that was terribly surprising. We know that these organisms change in the stream from spring to fall, but to see that quantitatively was reassuring. And in my 95% confidence ellipse around each suggests that, yeah, they are quite different. And they are highly correlated to the time of sampling, as you see here. So that justifies treating spring and fall data separately, which is what I've done. So by doing the same process, this time focusing just on my spring data, I have my reference sites in triangles and then my test sites in circles. They separate out fairly strongly along this conductivity or the specific conductance gradient with a correlation coefficient of 0.74, which again is not something I'm terribly surprised about. The reference sites are associated with lower conductivity over here, and then as you move up, you get test sites that are associated with higher conductivity here. However, what was surprising was to see this association, this correlation here with Julian day of sampling. So I mentioned that I had a pretty tight sampling window, only about 40 days, but even with that tight sampling window, I still saw separation within that window, which was a bit surprising. It's not a really strong correlation, but it is a significant correlation nonetheless. So that suggests that there may be some merit in considering how tightly samples are collected, because we know that the organisms are growing and some are leaving the stream throughout the year, so you may not get them in samples. So the time of sampling may be critical for doing really precise estimation techniques. And again, I did the same thing for the fall and saw a generally similar but less strongly associated relationship, which is why I focus on the spring data. So the next step that I needed to do was to identify the relative sensitivity of genera. So what I've done is I've taken that same ordination data set, and instead of the points for each site, I overlay the actual genera. And don't worry, you don't need to read all these text values, but all you need to know is that these Ephemeroptera that I mentioned, the Mayflies, they tend to group up toward the left of this center point, which is associated with lower conductivity. And so this x-axis, again, these numbers are basically arbitrary, but just know that the lower numbers here are associated with lower conductivity and the higher numbers here are associated with higher conductivity. And if I order the genera from associated with lowest conductivity up to highest, I get a rank of sensitivities relative to one another. And I've highlighted here in green the Mayflies, the Ephemeroptera. There are 8 of the top 20. So that's 40% of your 20 most sensitive genera are all in the Mayfly order. There are other organisms, as you can see here, that appear as sensitive as well, but as a group, as an entire insect order, they don't comprise nearly the proportion that the Mayflies do. Now, if I average, or excuse me, if I take the median of those values of ranks, I can look at the order level numbers. And as we see, based on what I just showed you, the Ephemeroptera come out on top with a median rank of 14, these guys here. And then Coleoptera, the water beetles, are right here. And then much lower ranked are the Plecoptera and the Trichoptera. These guys here that I mentioned at the outset were generally associated with pollution. They don't appear to be nearly as sensitive to salinity as do the Mayflies. And then down toward the bottom, generally insensitive are the Odonata, the dragonflies, the Oligochaeta, the worms, which are, they're aquatic earthworms, believe it or not, and the Megaloptera, which are like the Helgramites, for example. And then, oh, I'm sorry, I skipped the Diptera. These are midges. They're quite ubiquitous, but they're generally not as sensitive to salinity. Now, in order to determine what levels of salinity are likely associated with these community changes, I plotted out my data here with the, again, we're dealing with total richness. I'm sorry if that's not cut off. Total richness, which is the total number of genera. I have my reference sites in triangles, so they're generally higher than my test sites as expected. And I have a general downward trend. And as I mentioned in the US, there's no intrinsically good or bad condition. We can't figure that out. But what we can do is we can set societally deemed targets. And generally that is, we want things like reference or least disturbed conditions. And the way that's commonly done is to take the 10th percentile of the reference values. So that's what I've done. So I get about 22 genera as my 10th percentile of reference, and then anything below that is considered different from reference. And if I fit my generalized additive mixed model, I can find the intersection of those lines, and then I can interpret the conductivity associated with that. In this case, it's about 276 microsiemens per centimeter. And I can do that with my more sensitive metric for mayfly richness as well. 10th percentile of the reference values happens to be the bottom of it, which is about 5, which is exactly 5, actually, taxa. And then the GAM model fit and the associated conductivity with that, 284 microsiemens per centimeter. And I can do the same comparison. Again, these are with snapshot data. Okay, I can do the same thing with the prior monthly means that I talked about previously, in which I fit the models, find the same values. These values don't change. These 10th percentiles of reference are fixed because I only have the one biological level. But I can fit these different models and come up with different conductivity values that are associated with that. And I get a very similar plot to what I showed you before, but with different y-axis. So the y-axis is just this critical conductivity, the level of conductivity that's associated with leaving that reference zone, which is 276 I mentioned for total richness in the snapshot. And then if we look at the water quality for the 12 prior months, we can get different values. And for example, in September, we see 358 microsiemens is associated with the biology that's still here in the spring. And that makes sense because from our sinusoidal model, we know that September is roughly the highest level of salinity during the year, which makes sense that we'd have a higher number associated with biological change. And we can do that for our Ephemeroptera richness as well. Again, and I'm sorry, I forgot to mention, these are just confidence intervals that I got from bootstrapping. So we see that 284 based on our snapshot data. And again, in September, the roughly peak time of the year, we get a much higher number, 364. And this is in stark contrast to what's been done generally, wherein this value, 284, has been applied across the year as a target. And so these data suggest that there might be some merit in considering different values at different times of year to account for the fact we have temporal variability. So, in summary, I was able to characterize characterize the community response, but saw strong seasonal differences, which merits treating spring and fall separately, and that they were strongly correlated. Community differences in conductivity were strongly correlated. I found that Ephemeroptera taxa were generally the most sensitive group. And then of 9 community metrics, I just showed you 2 today, but of 9 total, they were all responsive and had moderate to strong fits with conductivity of both snapshot and monthly means. And then in determining the levels, I found that about 200 to 300 microsiemens was generally related to deviation from a reference condition based on snapshot data, which is it's a little bit lower than some findings out there, but considering that this is just on the cusp of change, this is like the 10th percentile of reference, it's not dramatically different. It's pretty reasonable as far as I'm concerned. And that monthly means, they can account for the variability that you just can't get from from snapshot data. So overall, going back to my objectives, what is the annual pattern of salinity? Well, clearly the high frequency data was able to reveal that pattern. That's something that we haven't been able to see before. And the sinusoidal model is a quantitative way in which we can predict that, either for management purposes or purely for research. If you want to know what these effects are, you need to be able to sample and understand when the two are related, both the biology and the chemistry. Second, can high frequency data provide a benefit over the snapshot approach? No, based on my data, if snapshots are temporally consistent, which I explained were quite exceptional. Alternative scenarios, there may be some merit there, but that's unknown at this point. And finally, how does the benthic community respond? Well, we see strong declines in richness and abundance with salinity, which is not generally surprising, but now we have some quantitative numbers associated there. We should have clear evidence that the Mayflies, again, the Ephemeroptera, are the most sensitive group, and that about 200 to 300 microsiemens is a level based off of spring snapshot data that may be indicative of change from reference. So with that, I'd like to thank all these wonderful groups and people. My study sponsors and technical support were invaluable, getting access to the mine sites and finding reference sites. I spent hundreds and hundreds of hours. I spent 260 sites to find 25. And then, so that was extreme. My committee, which has been extremely supportive and patient with me. I appreciate that greatly. I had a lot of great lab and field help, a lot of great graduate students and undergrads. We have the best undergrads, by the way, I must say. We've been very fortunate. And then, of course, the greatest moral support ever. Thank you, Autumn, and my daughter, Cora. So with that, I'd be happy to take questions. Species, no, I did not look at species. Generally, with these benthic macroinvertebrates, they spend most of their lives as juveniles in the stream, which is when we sample them. And generally speaking, species are difficult, if not impossible, to discern in the juveniles.
So you're confident you wouldn't see any differences if you were able to get that?
No, I mean, there may be some differences in species for sure. I can't imagine it would be huge numbers. A couple of different species, perhaps, for some of those genera. But this is the way it's done, by and large, is genus level for bioassessment. Yeah.
Unless I missed something, you were presenting all richness. Did you look at Shannon or evenness or anything like that? Do you think patterns would have changed if you looked at dominance or something?
Yes, Yes. Sorry. So the question was, I presented richness metrics, and the question was, did I examine other metrics such as Shannon, diversity, or evenness? Yes, I did. I mentioned there were 9 metrics that I examined in total. I did. Shannon diversity was a significant response variable, but it had a low model fit. I did not respond as strongly as some of those Mayfly metrics that I showed you. As well, I looked at evenness, which wasn't a significant respondent. The only evenness metric that seemed to respond was a percent 5 dominant taxa. So of the total taxa, what proportion of the individuals are made up by the 5 most dominant? Does that make sense? Yeah. So there was some response in evenness, but it wasn't a strong responder. And I think part of that, and that was generally the case, as you saw, my total richness metric was much more variable than my Mayfly richness metric. And I think all of that is for the same reason, and that is that the Mayflies tend to be the most sensitive, and most other taxa not as much. So it's not really an even response across taxa, it appears. Yeah.
It looked like the Betis was less sensitive within the Ephemeroptera. Any thoughts on whether that difference in sensitivity could skew, lumping Ephemeroptera into one metric, and maybe any ideas on physiologically why?
Yes, so the question is, I'll go back to the slide. The question was about one particular genus of mayfly. Let me just dim this really quick. One particular genus of mayfly is much less sensitive than others. So most of the mayflies group up over here. But then there's this one genus over here, the genus Betis. And Betis is known as a generally tolerant genus to lots of types of pollution. And in this case, yes. I'm glad you asked this question. What I have not shown you is my most strongly responding metrics, which were mayflies less genera from the family Betidae. So the family that comprises this genus, and I had one other genus, this guy right here, Acentrella, was also both quite ubiquitous among the mayflies in the streams that were salinized, meaning it was tolerant. And by excluding that family altogether from the group of mayflies, I got much stronger fits. I got R-squareds up to 0.79, for example. So yes, absolutely. And that is part of the reason that I did this exercise, because if you want to talk about the response to a stressor, it's really critical that you focus on things that respond to that stressor. Sure, knowing what doesn't respond to the stressor is very valuable in other respects, but when we talk about things like regulatory requirements for protecting species, you need to know the ones that are sensitive as well. So yes, so I did that analysis. I excluded those tolerant mayflies, and I got much stronger fits. Now, as far as why that is, the Betidae are evolutionarily different from many of the other mayflies. They branched off genetically millions and millions of years ago. And so there is, I don't know all the ins and outs of the physiology, but there is osmoregulatory differences. There are osmoregulatory, so the ability to regulate those ions in solution, pump the ions back and forth. So that's the suspicion as to why. And there's a lot of active research going on right now in the laboratory to understand those mechanisms. Yes?
Other than time, how does
That's a bit above my pay grade. The question was, other than patience and time, what does the mining industry do to mitigate these impacts? And just really quickly, the reason you mentioned time is because in the construction of these valley fills, there's a lot of rock material that's unweathered that just leaches out ions. We know it can last decades and decades and decades. And in fact, we just recently completed a study sponsored by the Office of Surface Mining, wherein we looked at trends over our study period of about 4 or 5 years. And we saw negligible trends, very low, maybe 20 or 30 microsiemens per year at the most, only in some sites, which is about 60 years to get to 300 microsiemens if that rate continues, which it probably doesn't. So in terms of mitigation, that's a great question. About the only, you can't treat the water. You can't put reverse osmosis stations in every hollow fill. That would be impractical. So I'm not really sure. There's certainly no evidence that I found in my work to suggest a clear option. Yes.
Yeah, Tony, that was really wonderful seeing all this. It's a really nice, integrated study. Your sinusoidal model of SC, which is really also a good thing to see, is obviously driven by seasonal differences in base flow and total discharge, and you've shown that. But if you look at the fall, September, October, you see all those points high, and then you see a much steeper decline than you're actually modeling here. Are you aware of a mechanism why all those points would be way above that curve in particularly September, October?
These here. I think that's simply an artifact of the way that this model is constrained. This is what's known as the question was, what might explain these higher than fitted values in September for the sinusoidal model? I don't have a lot of insight there except to say that I think it's because of the way the model is fit right now. The model uses a single sine and a cosine term paired. And this is what's known as a first harmonic model. You can add additional levels of harmony. So you can add you can add a second harmonic going to the second period, and then you can do the third period and so forth, which will change the shape of the curve. But for the first cut, I kept it simple. So that may be able to better capture those values. The other thing that's a bit constraining about this approach is because it uses a sinusoidal model, as you know, a circle must come back on itself. So this value must equal this value. And so it must be symmetric in that sense. So that limits it as well.
Physically what's happening there is the salts accumulate in the fills during the dry season of the year. And we always see a big flush of them in the first leaching events in September and October. And so that's what jacks up those points there physically.
Excellent.
And because they're high and sort of artificially high because of those leaching events in the fall, then it drops off faster on the end. And we've got other supporting data on that, so please go ahead.
Excellent. Thank you, Dr. Daniels. Just to reiterate for the record, the reason those are high is that the salts accumulate during low flow periods, and then that first fall rains flush out those extra concentrated salts, which then are subsequently diluted. So thank you. That's an excellent point. Yeah.
Yeah, very impressive and useful work. So essentially, you went about this in the way the regulatory agency is doing so, is an effects-based, right? Effects-based in terms of setting that criteria. I mean, how you get your target is somewhat reference-based using your dependent variable, but your independent variable, your specific inductance, is you're looking at the effects-based to that dependent variable, right? But of course, sometimes we use just a reference-based using that water quality variable. And so if you did that, would you think that you'd get a similar threshold? Does that make sense? Like if you didn't even look at the biological data and you took a bunch of reference streams and their specific inductance and you looked at the 90th percentile or 10th percentile and went with that approach, would you get a similar specific inductance?
Gotcha. So the question is, what I've used is an effects-based model, which is relating the biology to the water chemistry and using the reference condition of the biology to determine the target. The question is, if I did instead look at simply what is a reference level of conductivity, would I conclude that I've deviated from reference? And I would say quite possibly, because a recent study, I believe it was 2014, I want to say, EPA examined what they were trying to determine background conductivity across the United States, trying to determine what constitutes natural levels. And in this ecoregion, the Central Appalachian ecoregion, I believe they decided it was about 46 microsiemens. And they based that off the 25th percentile of all the streams they look at. And that's a pretty common procedure to determine what is a reference condition. So I will say, however, is they used one data point per stream per year, possibly, if that. So I'm not sure what time of year that 46 relates to. If it's here, it would make sense. If it's here, not so much. So that is one way that you could do it. You could say that, hey, anything above 46 is less like reference. I think the median value is about 100 microsiemens, so then you start getting farther and farther away from reference condition, and it tops out at in that 200 range nationwide. Yeah.
Could you argue why it matters if these mining impacted streams have fewer mayflies?
Why it matters? Yes, I can. Thank you, Ross. The question was, why do we care about mayflies? Mayflies are a quite ubiquitous and quite important group within the benthic macroinvertebrate community. In particular, the ones that are sensitive to salinity perform multiple functions in the ecosystem, the most notable of which is they eat the periphyton, the biological material that grows on rocks, for example. And they're called scrapers for that reason. They scrape that material off of the rocks. And so they serve the purpose of processing that energy source within these headwater streams. However, I will note that in these headwater streams, that's not a primary energy source because there's so much shade from the canopy that you don't get a lot of light, you don't get a lot of primary productivity relative to inputs of leaf matter into the stream, which is a major energy source, which I think there's been some research recently about that. Yes, that was also part of our OSM study. So the mayflies definitely provide that. They also provide a lot of biomass as a food source for downstream and local predators. Yeah.
You started with this global, all the headlines about salinization around the world. So how many of those other reviews dealt with coal mining?
None of the ones that I just showed you. Sorry, the question was how many other research efforts have been focused on coal mining? There have been quite a few, but they've been very regional for the most part. The EPA region that oversees the Central Appalachian area is Region 3, and they do a lot of work. They have done a lot of work. Greg Pond especially has been highly instrumental in identifying the relative differences between mining and residential and reference land uses in salinization, but nothing to this targeted of an effort. So like I said, when I mentioned that some of this stuff wasn't surprising, that's why. There's been good documentation that we have declines in diversity with increasing salinity. Mayflies in particular tend to be sensitive, but globally, it's not as prevalent. There's been a few studies here and there, but they've generally found similar findings. You know, the same types of ions, the sulfates, for example, get elevated, and we see generally declines in diversity there as well. Yeah.
In the coal mining impacted streams in Virginia, what would you say is the average specific conductivity? What would be the highest that you observe?
Oh my.
And related to following up on that, I mean, what do you think is the time frame, just, you know, based on what you think in terms of how long it will take for those streams to reach some normal, say 300 or something like that?
Okay. So two questions. One is what is some perspective on a typical conductivity level for coal mining impacted streams, especially in Virginia? And then the second question is how long do I think it will take for those streams to return to something approximating a reference condition? So to the first question, I couldn't tell you for sure. I didn't survey them all. In my data, I saw conductivity levels as high as approximately 2,000, 2,200 microsiemens, which is quite high. In fact, one of those streams I showed you the picture of was one of those as well. So that's kind of on the upper end. I think of my streams, I think the mean was much lower. It was somewhere around 1,200. And again, these are the headwater streams. So if you want to talk about downstream waters, there's a lot of dilution effects that occur, but there's also cumulative impacts. If you have a catchment here and a catchment here and a catchment here that all have those mining impacts, they can aggregate and have combined effects downstream. But in this case, dilution tends to keep those values low. As far as higher order rivers downstream, I don't know that I've seen anything approaching 2,000 for sure. It's probably much lower, 500 to 1,000 at the worst, I would imagine. And the second question, I'm sorry, the second question is time, decades for sure. Studies that Virginia Tech has done examining fills of various ages haven't seen anything approaching reference condition, even with fills that are decades old. 50 years, easy. A lot of it's hard to gauge too, because it depends on how much material, depends on what material is there, depends on the water infiltration, the chemistry. It's quite complicated.
Time for any more? It's just about 10 o'clock.
One more?
So
Last one.
You mentioned that draft guidance from EPA. What value or values do they have in that from the previous one?
Yeah, so EPA, the question is, EPA has come up with some draft guidance, so what do they recommend? They recommend a level of 300 microsiemens as a target everywhere. For mining. This is for the Central Appalachian region of mining. And again, that value is based on one sample in one stream, one time. That could be anywhere from March to October. And so it's unclear as to how that accounts for temporal variability, which was a major impetus for my work.